All right, let's talk a little bit about related rates. Now, before we get going, I'd like to take a moment to show you my fine artwork that I have here. I don't draw a lot, but I think we can all appreciate the intricacies of this particular piece. This is kind of one of your classic examples of related rates. This is a falling ladder problem. So we have a nice tall ladder, 13-foot tall ladder, and when you, let's say you walked away from it for just a second and it was leaning up against your house and, oh no, the ladder is whoosh, sliding down. So in this particular case, our 13-foot ladder is 12 feet, or is when X is 12, so is just about to hit the ground. So this ladder is sliding out there, so at 12 feet, the ladder is moving at 5 feet per second away from the wall. So we know that this x direction, the dx dt, is going to be 5 feet per second. So with that, we have two questions. How fast is it sliding down the wall? And how fast is theta changing? So with this, as we start looking at some of these, and I'm sure you'll find out real quick as you start to get into the homework, is that there's really not one set way to solve these. Each problem can be solved a lot of different ways. So this isn't the only way to solve this one, and that's one thing that's kind of nice about these ones, is that there's a lot of resources out there and there's a lot of different ways to do it. So this isn't really the only one, but it is a way to do it. So let's take a quick look here at how we might go. Let's start at how fast is the ladder sliding down the wall. So we're going to, at x equals 12, I'm just going to real fast, I want to figure out when x equals 12, what does y equal? Because that's probably going to be something that I'm going to want to know down the future. So that one is pretty easy. We have the old Pythagorean theorem. So we have 13 squared equals 12 squared plus y squared. So we can take our calculator here. And we got, let me slide it up so you can see it. Okay, so we're solving for y. So we're going to subtract 12 squared from 13 squared. So I've got 13 squared minus 12 squared equals y squared. So, and then I'm going to have to take the square root of both sides. So the square root of 13 squared minus 12 squared, that's going to equal 5. So I know that when x is 12, y is going to equal 5. All right, so that's useful to know. So now let's start setting this up. So speaking of the Pythagorean theorem, let's kind of use that as the basis of what we're doing. So I know that from this equation, I know that I have my 13 squared is going to equal x squared plus y squared, no matter what. So you might say, well, why did we just figure this out in here? Well, that's because this is just at this one particular instance that I wanted to know what this y would equal. But this is the case for any time. So any time that this ladder is falling, we can model it with the length of x and the length of y with this one equation. All right, so now let's differentiate this. Let's see how fast x is going to change and how fast y is going to change with respect to time if it falls. So, all right, so we'll take the derivative. 13 squared. Actually, that'll be d dt. Sorry. All right, so that equals derivative of x squared plus y squared. Okay. Well, now we have a little bit of implicit differentiation, which is no problemo. That shouldn't scare us too much. So on the left-hand side, I've got just a constant. So the derivative of a constant is just going to be 0. On the right-hand side, I'm going to have 2x times dx dt plus 2y times dy dt. All right. So, taking a look at this, let's start to utilize the things that we know in here. And we're going to start solving. So, how fast is the ladder sliding down the wall? Well, that's going to be this. So this is what we're going to want to solve. So let's plug in the stuff for everything else. Well, I know what my x equals. My x equals 12. I know what my y equals. My y equals 5. And I know what dx dt equals because they told me that this ladder is sliding away at 5 feet per second away from the wall. So that's how fast x is changing. All right, so that shouldn't be too bad then. We should be left with just one single variable. So I've got 0 equals 2 times 12 times 5 plus 2 times 5 times dy dt. All right, calculators out. 2 times 12 times 5, oops, that's a minus. 2 times 12 times 5, that equals 120. Plus 10. I'm just going to write this as y prime because it's a little bit easier. All right, now we're just going to subtract 120 from each side. So I've got negative 120 equals 10 y prime. Divide each side by 10. And I know that y prime is going to equal 12, or negative 12, I guess, feet per second. So I know that this ladder is sliding at this particular time, because we need the time, at when it's 12 feet, so when it's almost about ready to hit, if x is sliding away at 5 feet per second, y is going to be sliding down at negative 12 feet per second. Oops, you can barely see that. All right, so that's the first question. How fast is it sliding down the wall? Well, it's sliding down the wall, negative 12 feet per second. Now let's answer the second one that we asked, which is how fast is theta changing? So to do that, let me go ahead and go onto a new piece of paper here. And I'll kind of transfer over some of our stuff. So we had, remember, there's our ladder. This is kind of just the brief sketch so that we can help remember what it is that's going on. It's a 13-foot ladder, and we're looking for how fast theta is changing. We've got, here's our y, and here is our x. All right, so, and it's at this particular time. So just keep that in mind. It's when, so it's when x equals, oh, I already forgot. Apologize for 1 second. Let me, hey, you know what? Actually, this is going to make kind of a crazy noise. I got an idea. Look at this. All right, ready? I'm going to fold this over and fold it over one more time. Maybe this will work a little bit better. And one last thing. Sorry to take up your time, but I think this will be worth it. All right. Oh, boom. Look at that. Perfect. Okay, well, maybe one more fold. Sorry, origami here. All right, then that way we can kind of remember what exactly it is that's going on. Oops, just like that. Okay, there we go. Okay, so we're looking for how fast is theta changing. Okay, so let's write an equation then. So the equation that I'm going to start with, I know that cosine, ooh, that's a little bit, here, I'll take another pen. There we go. All right, so how fast is theta changing? Well, the cosine of theta, that's just going to equal my x over 13. All right, that's so that's because 13 is not ever going to be changing. So let's go ahead and take the inverse cosine of both sides. So I know if I wanted to write theta, I could write it as theta equals cosine -1 of x over 13. All right, so here we go. We have to use the chain rule. We got the outside and the inside function. So let's go ahead and take this derivative down here. And this is going to be d theta dx. So I know that theta is changing with respect to x of this is going to be. So I've got the cosine. Oh, I got to look that one up. I always forget. 1 over square root of 1 minus x squared. So x is just x over 13 squared times the derivative of the inside. So x over 13, that's just going to be 1/13. All right. Well, so here's our equation that we're looking at. And we have been given that we know when x equals 12 is what we're looking at. So let's go ahead and plug 12 in for x. And then we can see how fast it's going to be changing. Okay, so we bring our calculator over here. This is kind of a tricky calculation. I wonder if this is a... Nope, that's not going to work. Okay, so we've got 1 divided by... you need to see that. All right, the square root 1 minus 12 divided by 13 squared. All right, 2.6 times 1 over 13. Oh no. 1 over 13, there we go. So, it looks like, oh no, I made a mistake there. 1 over, that is just 1 over, so 2.6 times 1 over 13. There we go. That looks a little bit better. So 0.2. All right, so I know that d theta dx is equal to 0.2, but I'm not interested in d theta and how fast theta is with respect to x. I am interested in how fast theta is with respect to time. So what I can do here is I'm looking like I have, let's go ahead and write down here. I have d theta dx, but I also have been given dx dt. Now looking here, this is sort of just like a fraction. I can cancel out the dx's. So I'd be left with dx or d theta over dt, which is what I want. So let's go ahead and do this. D theta dx is 0.2. Then dx dt is 5. So I can say, how fast is this changing? Well, 0.2 times 5, that is just 1 radian per second. And I get that these from the radians is from this d theta over dx, and then the seconds is from this feet per second here. All right, so d theta, this is radians per feet, this is feet per time, so the feet cancel out, and I'm left with radians per second. So just keep an eye out on those units as you get it. And there you go. As you can see, you know, they can be a little bit messy sometimes, but hopefully this was helpful in just sort of seeing how you set them up. Again, like the answer to this one, you could have solved a number of different ways. You could have taken the sine, you could have done tangent, you could have done any of those. So hopefully this was helpful, and yeah, that's kind of just the basics of it.